In this unit, we're going to be looking at molecules in three dimensions. And one of the things that we're looking for is if there are these molecules that have some asymmetry to them. And we're going to be looking, as I said, we're going to look at them in three dimensions. And the reason this is important, a lot of students will look at this at first and say, well, why do we even care about this? If atoms are pointing in different directions, what does that matter? And I think rather than kind of bury the lead and say why this is important at the end of the chapter, I'm going to talk about it why this is important at the beginning of the chapter. Um, and so let's take my first example I want to look at is something that everybody's familiar with. We've all heard of the compound ibuprofen. Ibuprofen exists as a pair of what are known as stereoisomers. That's a concept we've touched on very briefly in our last unit. Um, but with ibuprofen, the only difference between one stereoisomer and the other one is this carbon right here. In this isomer of ibuprofen, that CH3 is going away from you. And in this isomer, the CH3 is coming out at you. Now, for right now, kind of, take my word for it. Well, I'll show you how you can prove this in a little bit, that these are not identical compounds. I can't just simply turn one compound around and get the other. And I'll demonstrate why in just a little bit. But there's another way that we know that these are not the same compounds by their biological activity. S-ibuprofen, I'll talk about S means a little bit later. S-ibuprofen is biologically active. Okay. Ibuprofen is a non-steroidal anti-inflammatory drug. And so it helps alleviate fevers, aches, pains, all of that, stuff that you want to kind of, suppress. And S-ibuprofen is biologically active. Your body recognizes it and it has the biological response we would expect. Our ibuprofen, though, however, is inactive. Nothing happens if you were just to take pure R-ibuprofen. Absolutely nothing would happen. Your body doesn't respond to it at all. And so it just kind of emphasizes just that different orientation around that single carbon in three-dimensional space causes ibuprofen to be active or inactive. A more drastic result, and kind of less known, this was an issue, I think, back in the 70s, 60s, and 70s, um, is this compound thalidomide. Now, again, like ibuprofen, thalidomide has two stereoisomers that only differ around the orientation of that carbon. So in R-thalidomide, the nitrogen group's coming out at you. In S-thalidomide, it's going away from you. So again, you might say, all right, big deal. How is that going to make it any different? Thalidomide was originally prescribed to pregnant mothers to alleviate morning sickness, and R-thalidomide did just that. But it wasn't discovered until the drug had been on the market for quite a while that S-thalidomide, which was made in conjunction with R-thalidomide, scientists either didn't, or the chemists, or didn't know they were making the other stereoisomer, or they just didn't test it individually. But S-thalidomide caused birth defects in the developing baby, and about 70% of the time led to the child being stillborn. So obviously not a great thing, but this is just, a couple of examples illustrating why we care about stereochemistry and why this is important. If you take biochemistry, you're going to see even more examples of this in action. Now, this whole chapter is based off of this concept of chirality. Now, chirality, when we apply this to chiral objects do not have any symmetry. And chiral objects are not identical to their mirror image. So what I want you to do, and maybe I'll enable my camera real quick so that you can see what I'm doing. Nope, sorry, I don't have my camera hooked up right. Never mind. What I want you to do is take your two hands and face them toward each other. And you'll see that your palms are facing each other and your hands are mirror images of each other. But you can't take one of your hands and lay one down flat, palm on top of the back of your other hand, and have all your fingers line up. I mean, maybe the middle finger is the only one that lines up, but you'll find that your thumbs are aligned with your pinkies, and your pointer fingers are aligned with your fourth finger, and it does it. None of there is not any symmetry when you put one hand on top of the other. And so chiral objects are not identical to their mirror images. Now, what are some things that what are some examples of symmetry? The easiest way to, especially with compounds, to identify symmetry is you want to cut the molecule in half. And if both halves look exactly equal, now when I say equal, that means same atoms going in the same direction. Then that means there's some sort of symmetry. So like this compound here with the bromine and chlorine, if I cut it in half right down the middle in this way, so you can kind of see there's like, half a bromine, half a chlorine, and a hydrogen right there. And then there's on the bottom, half a bromine, half a chlorine, and a hydrogen there. And those hydrogens are both kind of going back away from you. So same atoms going in the same direction. So we would say that this object is achiral. The prefix a there just means not. So you cannot have a chiral compound that has symmetry in it. Or this example here, if I cut this ring down the middle like this, I see on one side there is that group. I have the identical group on the other side, and all of the atoms are equal. There's no difference. And they're also going in the same direction. Now let me contrast this. I'm going to change this just so slightly. I'm going to make this a methyl group, and I'll keep this an OH. Now if I cut this compound down the middle in the same spot, there is no longer any symmetry because this is different. Those are different atoms than this. And so this would be a chiral object. This would be an achiral object. So let's kind of, again, start applying this to molecules. Now this will go to the hand example that I did on the previous page. We're going to look at this compound here, CH3CHBrCl. And I want you to look at the diagram on the right. So let's call this the CH3. We'll call the red one hydrogen, the purple one here bromine, the blue one here chlorine. So we have CH3 and then hydrogen, bromine, and chlorine. Now we can take those two molecules and have them look like they're looking in a mirror. The hydrogen sticking out into the mirror, the methyl group is going up, the bromine's coming out at you, and the chlorine's going away from you. Okay, so those two things are mirror images. Now, in order for them to be stereoisomers, they cannot be superposable. Now, what does that mean? That means I can't take one of them and put them on top of the other. Okay, so and I highly encourage you to, if you have a model kit, make two of these molecules exactly the way that you see them on the screen and try to put them on top of each other. When you do that, like as shown here, you see that, yeah, you can get two groups to line up, but the others don't. They do not line up completely. You need everything for them to be superimposed. If you did put them on top of each other and they superimposed completely, then they would be identical. So these two compounds are not identical, even though they have the same atoms connected to the same carbon, but their orientation in three-dimensional space is different. That's why we call them stereoisomers. So these are two molecules that have a different orientation in three-dimensional space. Now, if these stereoisomers are non-superposable mirror images, then we call those enantiomers. That's our first type of stereoisomer we're going to cover in this chapter. We actually spend quite a bit of time talking about. So um, if you have non-superposable mirror images, those are known as enantiomers. Now, before I dive deeper into this, let's talk about um, finding what are called chiral centers or and stereocenters. Now, a stereocenter is a point at which the exchange of two groups leads to a different three-dimensional space. Okay, think back to like cis-trans isomers from our last unit. I gave this example of the cis isomer of 1,2-dimethylcyclohexane and the trans isomer. That should be solid wedge. So what I literally had to do is take this carbon here, this methyl, and this hydrogen, and switch places with them. So now the hydrogen is here, and that methyl group is there. And that led to a different orientation in space. So we would call this carbon right here a stereocenter. We could also call the other one a stereocenter as well. We will see this soon when we start talking about alkenes or molecules with carbon-carbon double bonds, that it's possible to have a stereocenter with these double bonds. If we look at this isomer here of 2-butene, if I were to take this methyl group and this hydrogen, notice how this methyl group is oriented to the one over here. They're kind of in opposite directions. If I were to physically take those two groups, the CH3 and the hydrogen, and rip them off, switch places with them, now they're in a different orientation in three-dimensional space. And so we call those things stereocenters. Now, a special type of stereocenter that we're focusing on this chapter is known as a chiral center. These are atoms, and like 95% of the time, that's going to be carbon, with four different groups bonded to it. Circle, highlight, star, like that um, phrase right there. This is an atom that has four different groups bonded to it. Now, that means it must be sp3 hybridized. So sp2 carbons cannot be chiral. sp carbons cannot be chiral. And another thing to note, because it has to have four different groups, CH2s and CH3s can never be chiral because CH2s have two hydrogens, CH3s have three hydrogens on it. So that's a little mental note to make, something you always want to keep in the back of your mind. So if we take a look at this compound drawn below, this alcohol here, focus in on this carbon, this second carbon. So first thing we're going to do is, does that carbon even have four different groups around it? So I have a CH3 over here. I have an OH, I have an H, and then I have a CH2, CH3. So we treat carbon chains as different as long as the lengths are different. So this is a one carbon chain over here. That's a two carbon chain over here. They're different groups. Now notice how that OH is coming out at you and the hydrogen is going away from you. If I were to physically rip those two groups off and spin them around, put them in the opposite direction, I get the enantiomer of, of the original compound. So that's why we call this, not only is it a stereocenter, but it's a chiral center because it has four different groups. Now, one thing I want to highlight before moving on, some kind of notation. So we're going to be using these dashes and wedges a whole lot. And one thing I want to point out is that it's quite common to see something like this, where one group on that carbon has a wedge to it. So in this case, a solid wedge. You can automatically assume that the last group here is the hydrogen you don't see, that it automatically has the opposite wedge. So whether that OH starts out here like with a dashed wedge, you can assume if you don't see another wedge that the hydrogen you don't see is automatically the opposite wedge. So that is convention. That's like a standard for representing these molecules. So let's do some examples. Oh, actually, I want to back up. Sorry, I forgot this one thing. Um, One thing I want to point out is that all chiral centers are stereocenters, but not all stereocenters are chiral centers. So, well, how does that work? Look back at this example of the alkene up here. This carbon right here, actually both of these, they're both stereocenters, but since they don't have four different groups around them, we cannot call them chiral centers. Chiral centers, the definition is it's an sp3 hybridized carbon with four different groups around it. So that's why that statement down there is true, because all chiral centers are stereocenters, but not all stereocenters are chiral centers. So what we're going to do in these problems is identify find stereocenters and then kind of label them as chiral or if they're just a regular stereocenter. So let's start with the first one. And I'm going to kind of go like look at each carbon. Eventually, you're going to get to the point, if you practice this enough, where you can kind of look and say right away, oh, I'm eliminating these possibilities. So I'm going to kind of talk about all of these all at once right here. All of those groups there are CH3s. And so if we use that rule of thumb I gave you on the previous page, CH3s cannot be chiral. Then if I look at this carbon right here, this is a CH2. CH2s cannot be chiral. So that kind of leaves me with this, this, and this as potential chiral centers. So let's look at the first one. I'm going to call this carbon A so that we can talk about it. If you look at carbon A, for it to be chiral, it has to have four different groups around it. So if I look at this group, that's a CH3. If I look at this group, that's a CH3. So I'm not going to even bother looking at the other two groups. I have two of the same groups there. That can't be chiral. Okay. So I'm going to kind of clear some of this off just to make it look a little bit neater so that we can look at the last two carbons. So I'm going to call this one B. So if you look at B, let's try to find four different groups around it. Well, I'm going to draw on the hydrogen. And so I have bromine. Okay. That's one group. Hydrogen. That's another group. If I go this way, I hit like a CH2 and then all of this other stuff. If I go this way, what do you notice? Well, it's still a carbon, but it's a CH and it looks different than the other group on the other side. So there are four different groups around carbon B, and so that makes it chiral. So there's a chiral center. Now, if I look at the last one here, I'll call this carbon, I won't call it C, I'll call it D, just so that we don't mix it up with carbon. Um, if I go this way, there's a methyl. If I go this way, there's also a methyl group. Two of the same group disqualifies that from being chiral. So the only chiral center is carbon B. Now let's take this one step further. And let's say I ask you to draw a pair of enantiomers. Okay, so let me show you how that you can easily do this very quickly. Pick your favorite wedge and make that your chiral center. Now, it doesn't matter if you start with a solid wedge or you start with a dashed wedge. Just pick your favorite one and start there. The easiest way to draw an enantiomer, now you can try to draw its mirror image. So you can imagine, okay, there's a mirror here, and I'm going to try to draw it looking exactly like it's looking in a mirror, like that. You could do that. Now, that works, it's easy-ish for small molecules. But if you're drawing very large ones, it's super difficult to near impossible to try to draw a mirror image like it's looking in a mirror. The easier way is just flip two groups around your chiral center. So make everything the opposite wedge. If that bromine has a solid wedge, give it a dashed wedge. Because it's assumed that the hydrogen you don't see has the opposite wedge. And so this one would have the opposite wedge. So you just take two groups around your chiral center and flip them. If the compound, I know this example doesn't have it, but if there are more than one chiral center, flip all of the chiral centers to make the enantiomer. I'll do examples of this a little later, but I'm just kind of foreshadowing where we're going to be going with this. All right, so let's look at the second example here. Now, again, we kind of go through the whole thing. CH3s can't be chiral. They can't be stereocenters because they have three of the same group on them. Now, we do have a double bond, so there's the potential for the carbons of the double bond to be stereocenters. They can't be chiral, but they can be stereocenters. I'm going to draw on the hydrogen. That's understood to be there. Now, if I try to flip these two groups, do I get a different orientation in space? And the answer is no. If I flip methyl with methyl, I just have a methyl on top and methyl on the bottom. Now, if I try to do that to the other side, with the hydrogen with the chlorine, what does that look like? Well, let's draw the result. Is that any different? I'm just gonna kind of pause for a second. I want you to look at that. Is that a stereocenter? Let me give you a hint. Flip this molecule over. What do you get? You get right back to the original one. So these two structures are identical. So this compound does not have any stereocenters in it. And that's okay. Like, not every organic molecule is going to have a stereocenter. Not every organic molecule is going to be chiral. So you don't have to be surprised if that happens. Okay, let's look at this third one and see if we can find any stereocenters. So again, kind of make it easy on yourself. Right away, eliminate any CH3s, eliminate any CH2s, because those can never be chiral. And you say, well, wait, there's a nitrogen there. Can that be chiral? If it's sp3 and it has four different groups around it, absolutely. It doesn't have to be carbon. It's just most of the time in OChem, it's gonna be carbon. Because that nitrogen has four different groups around it. You got a hydrogen, there's a methyl on one side, there's an ethyl on the other side, and then there's a propyl group as the fourth group. So that nitrogen is chiral. And I can draw a pair of enantiomers for it. I can say, well, maybe that methyl group here has the solid wedge, the hydrogen has the dashed wedge. And if I want to draw its enantiomer, all I got to do is, excuse me, flip the wedges. Make the hydrogen solid and the methyl dashed. All right, now the last one here, this last one's kind of a little bit of a trick question. We know the CH3 and the CH2 can't be chiral. But if we look at this nitrogen, you got a hydrogen, a methyl, and an ethyl, and a lone pair. Technically, that lone pair is a group. So, yes, technically, there are four different groups around that nitrogen. Here's why this is a trick question. That this nitrogen is, they call it, it's like rapidly flipping or rapidly exchanging two groups because this is just a lone pair. So that lone pair might be up here sometimes. Sometimes it can flip around here and the hydrogen will go up here. So at room temperature, it's constantly flipping. So trying to resolve a pair of enantiomers of this is impossible. And so we basically say that even though there's four groups here, this is an example where this compound or that nitrogen would not be chiral. I just wanted to point that out because some students will come up and ask and say, hey, that nitrogen technically has four different groups around it. Yes, technically it does. But because of the way that lone pair kind of floats around, it could be in one place or another, and it does this rapidly at room temperature, so you can't really resolve it into an enantiomer. So chemists just say, okay, let's just we'll just say it's not chiral just to make it easy. All right, so just look at some like logistical things about chirality. Molecules with one chiral center are always chiral. Now, the examples I did before, we were looking at individual chiral carbons. And so if there's one chiral center, I'm talking about one and only one, then we would say the whole molecule is chiral because there is no symmetry. So this carbon right here, marking with a dot, you got a methyl on one side, ethyl on the other, propyl over here, and a hydrogen you don't see. That has four different groups around it. So we say the carbon is chiral. We say the whole molecule is chiral. Now, molecules without a chiral center are most of the time achiral. That most of the time is a very, very, very rare exception that we will not see, or at least I won't cover in OChem. Um, but there are certain times where you can have a compound that doesn't have chiral carbons, but yet the whole thing can be chiral. That's not something we will cover in this course. So an example of something that does not have chiral centers, kind of like this. And in fact, I'm going to kind of make it a little deceptive here. I'm going to make that methyl group have a dashed wedge. And I do that because I want to point out that just because I show direction with a group, I give something a dashed wedge or a solid wedge, don't automatically assume, hey, it's chiral. Okay. I'm just representing it in three dimensions. Because if I look at this on one side, there is a propyl group. On the other side, there's a propyl group. Two of the same group means that that carbon is not chiral. And so the whole molecule, because the whole molecule doesn't have any, there aren't any chiral centers, the whole molecule is achiral. Now, the last statement's kind of like a little um, interesting because molecules with more than one chiral center may or may not be chiral. All right, great. Like that doesn't really tell me a whole lot. You have to look for symmetry. For example, look at this second structure here. You have two chiral centers. That carbon is chiral, and this carbon is chiral. Now, I encourage you, if you're like, wait, how is that? Pause the video and identify the four different groups. Now, does that mean this molecule, the whole thing is chiral? You have to look for symmetry. What's the easiest way to do that? Cut the molecule in half. You can do this like top to bottom, left to right, diagonally. In this case, if I cut it in half from left to right, what do you notice about the two halves? The top half has the same exact atoms as the bottom half. Same atoms going in the same direction. That's the definition of a plane of symmetry. This molecule has symmetry. So even though there are chiral carbons, the whole molecule is achiral due to symmetry. Now, if I look at the first one, I have a chiral center right here, four different groups, a chiral center right here. If I cut it in half, does the top half look exactly like the bottom half? I mean, there's a couple things that are similar, like this is the same and this is the same, but the whole thing, you don't have the same atoms going in the same direction. So there is no symmetry here. So this compound has chiral carbons and the whole molecule is chiral. All right, I'm going to come back to this type of example here where there's chiral carbons but the whole molecule is achiral because of symmetry. We give that a special name. I'll talk about that in a little bit. All right, so let's do some practice here. Are these molecules, so we're looking at the whole thing, are they chiral or achiral? So what are the qualifications for, a whole molecule being chiral? Have to have at least one chiral center, at least one, and no symmetry. So let's look at the first one here, which is just plain old cyclohexane. So ask yourself, do I have any chiral carbons? Well, go back to that kind of um, tip that I gave you. CH2s and CH3s can never be chiral. These are all CH2s and cyclohexane. So since there's no chiral centers, that whole thing is achiral. Now let's look at the middle one here. Now, right away, students get drawn to this and say, oh, there's wedges. That's automatically a chiral center. Well, look carefully. And rings get really tricky when trying to find chirality. You literally like kind of what you have to do is take a couple of fingers, go in opposite directions. I go here, I hit a CH2. I go here, I hit a CH2. Okay, no difference yet. I'm going to keep going. And then I go here, I hit a CH2. And then I go here, I hit a CH2. Okay, still no difference. If I keep going, I hit this point here, and then the other direction hits the same exact point. Did I hit any point of difference along the way as I went around the ring in opposite directions? I did not. And so even though I drew the bromine and the hydrogen with wedges, this is different, but all of this is the same. So I do not have four different groups around that carbon. No chiral centers, means this whole compound is achiral. Now let's look at the third one. Okay, so again, let's go through like what does it mean for a carbon to be chiral? Well, I can eliminate these carbons because they're sp2. A chiral carbon has to be sp3. And I can eliminate the rest of these because they're all CH2s. So no chiral centers means this whole compound is achiral. Now let's look at the fourth one. Again, just because you see wedges or you don't see wedges does not automatically mean the compound is one designation or the other. What you're looking for are carbons with four different groups. So I'm going to eliminate first the things I know can't be chiral, like sp2 carbons, and CH2s can't be chiral. So I have one left here. And just so that I don't miss it, I'm going to draw on the hydrogen that's assumed. So bromine is different than hydrogen. And again, rings get tricky. So I'm going to go one atom in each direction to see if there's a difference. So when I go to the right, I hit a carbon involved in a double bond. When I go to the left, I hit an sp3 carbon. Yes, they're both carbons, but they're different kinds of carbons. So this is a different group than this one. So this carbon right here is chiral. There's only one chiral center. That means the whole molecule is chiral. Okay, let's look at the middle one here. So again, kind of quickly go through, eliminate the things you know can't be chiral. That means CH3s and CH2s. So let's start with the bromine there. And I'm going to draw on the hydrogen we don't see. So bromine and hydrogen are different. I got a methyl group on one side and then this other very long carbon chain on the other side. So that's four different groups. This carbon is chiral. Now let's look at the other carbon here. So this is the one we hadn't like really decided on yet. Does that one have four different groups? Oh, I'll draw on the hydrogen here. If I go this way, I hit a CH3. If I go this way, I hit a CH3 as well. It doesn't matter that I drew that with a solid wedge. It doesn't automatically make it chiral just because I drew a wedge. I'm just telling you what direction that carbon's going in. So that carbon is not chiral. But since I have at least one chiral center, the one I highlighted there in green, that's going to make the whole molecule chiral. Now, let's take a look at the last example here. So I'm not even going to consider these. They're CH2s. So let's start here with this one. And I'll draw on the hydrogen we don't see. So I have fluorine and hydrogen. Again, with rings, they're tricky. So I go one carbon in each direction. There, that's a CH2. When I go the other way, I hit a carbon with a fluorine on it. So those are two different groups. This side is different than this side. So that's going to make this carbon chiral. Now, for the same reason, that's going to make the other carbon chiral as well. Now, just because I have two chiral centers doesn't automatically make the whole molecule chiral. I have to, if it's greater than one, I have to look and see if there's any symmetry. So if I cut the molecule in half from left to right here, what do you notice? I do have the same atoms, but they're not in the same direction. In the top half, the fluorine is going up. In the bottom half, the fluorine is going down. So I have to have same atoms in the same direction in order for there to be symmetry. So the result, no symmetry, which means the whole molecule is chiral. All right, that's where we'll stop with this video. In the next one, we're going to be looking at how we name chiral centers. So this kind of goes back to the examples I was giving at the very beginning of this lecture. You notice that there was like an R and an S next to the names of those particular stereoisomers. Um, we're going to go into how those names came about.